Welcome back. We're going to continue our discussion on the effect of electrophilic substituents on an incoming substituent. So we looked at one example. I got three more examples. So with the help of all these four different examples, you would get a wide variety of idea on how things work. All right. So this is what you're already starting with. So you already have an electrophile attached to a benzene ring. Now we didn't look at a mechanism for this, okay? Because this is part of the aldehyde, and I want to reserve some things for the actual topic when we discuss those particular functional groups. So this is an aldehyde. This is a functional group. So if you look at that table, this is a meta-directing substituent. Okay, so that means what I'm trying to tell you is if this is your substituent, the incoming electrophile from this can only go to this or this. You can write it on one side or the other. You don't need to do both products. I always prefer to do my right side, okay? This is a meta-directing group, okay? And we know from our nitration reaction, HNO3 plus H2SO4 gives NO2 plus as the electrophile, plus your base, right? Now the electrophile is the one that would have to go to the meta position, okay? Now you don't need to draw a mechanism for it because this is merely attaching an additional substituent. But if you want, you can be more creative based on what I have taught you before. So you don't need to do that. So this is your starting material. Now, there are two meta positions, so the NO2 plus can attack here or here, right? Here or here. I'm only going to attach to this side, to the right side. Don't attach both on the same compound, okay? That has a completely different meaning than when you attach it one at a time, okay? You can attach it on this side or on the other side. Don't attach them both on the same molecule. That has a completely different meaning, okay? Remember, this is our substituent. So these are your ortho positions, right? These are your ortho, these are your meta, and this is your para, right? But a meta-directing group can only direct an incoming nucleophile only to the meta-directing group. So that means I'm just going to get rid of the O's. Okay. So I have a clean product. So let me get a different color and box this. Okay, so it all depends on the nucleophile. In this case, this is a meta-directing group. So with respect to the substituent, these are the two meta-directing positions. So you have to know this. This I cannot emphasize. You just have to go back to each of the 5 reactions and learn what is the electrophile, what is the one with the positive charge. You do have to remember that because, I mean, it may look like an alien concept now, but as you get to do more of this, it will seem to make more sense. Okay, so that's the first example. Now here is something very interesting, competing substituents, okay? Let's say you have 2 substituents already. In the previous case, we added one substituent to an already existing substituent. Let's say we've done it twice now. We have two substituents. One is your methyl, and the other is your NO2, right? They're both substituents on your existing reactant. So we know that our methyl is orthopara, okay? Your NO2 is meta. Here's very, very important. Pay very close attention to the way I put my colors, okay? I am going to actually give different shades. For methyl, which is this, with respect to the methyl, okay, I'm going to overlay it in red, okay? Okay, with respect to methyl, these are your ortho, okay? And this is your para, because it's only an ortho-para directing group, right? Now, this ortho position is already taken by the NO2. So With respect to the methyl, only the ortho and the para is available. With respect to the NO2, I'm going to give it a different color. Actually, I can retain the blue itself because with respect to the NO2, this is your ortho, right? And this is, well, this is your ortho, this is your meta, and this is your para. You see how things are different? Now, with respect to the, well, we know that with NO2, it only goes to the meta position, so we might not even need to worry about the ortho here. Okay. Although I was only pointing out that what that is, because NO2 is a meta director. So this is meta, this is also meta, this is ortho, this is para. Well, now the question is, who wins the race? Okay, whichever one is a larger of the two wins the race. So NO2 is a much bulkier group over CH3. Okay, so it can only be one of the two meta products. Okay, it's this or this, right? But this gives best of both worlds, right? With respect to this is para and meta, this is meta and ortho, right? So you can have two products, right? You have your CH3, you have your NO2, right? This is where you start with, okay? Now the Cl, which is, well, Cl2 plus FeCl3, if you remember, it will be Cl plus FeCl4 minus. So your Cl plus is your electrophile. So the electrophile could technically go to one of the two meta positions, okay? This or this, right? They're both meta with respect to, this is meta with respect to the NO2 here. This is meta with respect to the NO2 here, okay? Because these are two orthos. But this is also para, right? For the methyl. This is also ortho for this, right? So with respect to these, you know, this, you can have the Cl here, or you can have the Cl here. Okay? Because with respect to the NO2, these are the two meta positions, right? So the meta positions win the race. At this point, you don't need to even worry if it's ortho or para with respect to the methyl, because NO2 is a larger group and it wins the race. So you only have to give preference to the NO2 with respect to the NO2. These are the two meta positions. So that's where the Cl would go. So I've attached one of the Cl to this dot and the other Cl here. Okay. So this is competing substituents, means if you have two substituents, then the third has to go to one of them wins the race. Okay, let's go try this again. Okay, here you have CH3 and Cl. Okay, CH3 is ortho and para. Cl is also ortho and para, right? So with respect to the CH3, this is ortho and ortho. With respect to the Cl, this is also ortho, and with respect to this is also ortho, with respect to Cl. And with respect to the CH3, this is para, and with respect to Cl, this would be the para. Okay. So if you notice, the Cl2 plus FeCl3 would react, and then it would make Cl plus FeCl4 minus, right? Cl plus is the incoming electrophile. Now, the incoming electrophile could go to any of these three positions, okay? But this position is hindered because it's already got two groups on either side. So the incoming nucleophile is less stable because it's difficult for it to go between the two groups. So this position is highly unfavorable. So we can only have the other two possible. Okay. Sorry about my terrible drawing with the benzene rings. Okay. It's very difficult to draw these with these pens. So that's one of them. Or you can have this. Why we can have this is because of steric hindrance. Okay. It's because of the bulkiness of the two molecules, right? So these are the two products possible. All right, let's continue. Got one more example, I believe. Okay, I guess that's pretty much it. So I'd like to take the moment to summarize everything. So what we have done is we've done two separate things through these videos. First, we learned how to add a basic electrophile to a benzene ring, okay? And we learned 5 reactions: alkylation, acylation, nitration, sulfonation, and halogenation. And then what we did is, okay, now that we have learned how to add an electrophile to a ring, so now it's a matter of what does the added electrophile does to when we try to add another electrophile, okay? So when you add your first electrophile, we'll call it a substituent. So what if you try to add another substituent to an existing substituent, or you add 2 substituents? What happens when you try to add the third? Okay, so that's kind of what we have learned here as far as the major topic of aromatic electrophilic substitution. Okay, now we have to do more examples to really understand the competing substituents. Although if you have the table with you, I think it makes life a little easier. All right, so I have a couple more miscellaneous content that is very important. It's related to this topic, but it could also fit into any other chapter. I will make a separate video, and when I make it, I'll let you know. You do have to watch them. It will be part of the sequence. But I think it's very fluid that it could go into almost any of the other chapters. But I do like to bring it ahead of time so that whenever you see that related concept, you would see that knowledge is very helpful. Having that knowledge is very helpful. All right. So stay tuned for more videos.